All right, so we're going to switch gears and talk about seismic anisotropy and mostly go in the transition zone. So I know this is a slide from Jean-Paul's talk. So I know he introduced the concept of seismic anisotropy and also how we can determine it from surface wave data. He introduced the concept of radial anisotropy, which is the difference between vertical and horizontal direction in terms of which one is the fast direction for seismic wave propagation, and azimuthal anisotropy, which is in which azimuthal direction is seismic waves traveling faster. And we've explained to you that mapping seismic anisotropy is a really powerful tool to try to understand mantle deformation, because we can try to map it into mantle convection, mantle flow, and at least for the very top of the mantle, where olivine is dominant, we believe that the origin of the observed seismic anisotropy is due to lattice-preferred orientation of olivine. And generally speaking, in most cases, we think that the fast direction for seismic anisotropy represents the direction of flow or shear, probably more precisely. So now, where is seismic anisotropy inside the Earth? Jessica gave you a really nice talk about seismic anisotropy in the inner core and how complicated it is. I think Maureen talked about seismic anisotropy in D double prime. We have observations from shear wave splitting, pretty localized. There are some models, global models, that show anisotropy at the global scale in D double prime. I'm personally not convinced that we know for sure yet that it's global. And then, of course, in the crust, in the lithosphere and asthenosphere, there's plenty of evidence from a variety of seismic data that there is seismic anisotropy there. Now, how about deeper? The deep upper mantle, mantle transition zone, the top of the lower mantle. That's where it gets trickier. As we're going to see, I'm going to show you a few models, a few results from previous studies, and then I'll show you my own results. So this a slide from Maureen. We know that from shear wave splitting, there is more and more evidence in the last few years that there is seismic anisotropy in the slab or just around the slab, around the transition zone depth, top of the lower mantle. And so it's important to try to understand and try to get more and more and better constraints on seismic anisotropy at these depths, not only to understand slab deformations and deformation of the mantle near the slabs, but also it relates to this long-standing question. So that's a simplistic cartoon showing the two end-member models of convection when we might have, we might have layered convection or all mantle convections. Now, obviously, the truth is probably somewhere in between. But the transition zone, or the top of the lower mantle, maybe the 1,000-kilometer depth, might play a role in here. Now, seismic anisotropy in reference models. So because these are one-dimensional average models, there is no azimuthal anisotropy by definition. We average over all azimuths. But we can introduce radial anisotropy in reference models. And PREM, which is shown in black here, was, I think, the first one to include radial anisotropy in the mantle. And so we see that we had a strong anisotropy in the top of the mantle, and it decreased linearly with depth down to 220 kilometers depth, where there is a seismic discontinuity in PREM, the Lehmann discontinuity, and then it was zero, no anisotropy in this convention. When psi is 1, it means VSH equal VSV. There's no anisotropy. Since then, there's been a few models that have tried to provide better constraints with different types of data, sometimes including normal modes, surface waves, higher mode surface waves, waveform inversions, including body waves, and so on. And you see that most models agree. The anisotropy is strong in the top of the mantle, then it decreases, though some show that there's an increase an increase with depth down to 100 kilometers depth, then a decrease. But generally speaking, it's pretty strong there, then it decreases. Between 200 and 400 kilometers depth, it's pretty small. There's two models, the green one that's SEM from Berkeley, right? And the light blue one, which is from the Utrecht group, Visser. They do have some stronger anisotropy above the transition zone. Then once we enter the transition zone, again, very, very little anisotropy. Most of these models are on the right of Prem, so that's VSH larger than VSV, but barely anything, less than 0.5%, so probably lower than the uncertainties on these models. Now, the purple model was from a study by Jean-Paul, and then the blue one again from Visser. Now, they show stronger anisotropy, between 1% and 2%, but they also show very different signs, completely opposite signs. So which one is it? Is it that we have anisotropy or not? And if it is there, is it fast horizontal waves or fast vertical? So that's still a question that we don't have an answer for. Oh yes, I have this slide to show that the Visser model was based, as opposed to all the other ones that were coming from regularized inversions. This one was based on a model space search. If you remember Vet's talk, he talked about this type of methods. So they had uncertainties on their models, and even including uncertainties, their data was showing that VSV is larger than VSH. Now, when they did this study, they inverted. They used love and Rayleigh wave, fundamental and higher mode separately, which means they inverted the love wave and the Rayleigh wave separately, then combined them to get an estimate of anisotropy. And they introduced some prior assumptions, like most studies, on the least well-resolved parameters. In 2006, that was a study from my PhD, we had done something similar, slightly different model space search technique, in which we had inverted love and Rayleigh together. We also had fundamental and higher modes, but that was an older data set. We had not imposed prior constraints on the least resolved parameters. We were trying to look for everything, see if what was coming out of that. And we also, because I only had one processor at the time, and these techniques are very slow, we had to assume a priori that there was no anisotropy at all in the bulk of the lower mantle. But the result was that we had these distributions of anisotropy, so that's depth increasing from the top to bottom, radial anisotropy. In my convention, negative means VSH larger than VSV. And if you look at what we have in the transition zone, the likelihood of the largest likelihood of anisotropy was in VSH larger than VSV. So different than the Visser and Trumpet results. Yes. So they were mostly the fundamental and higher modes from the Oxford group, Van Heist and Woodhouse, from 1999. No, oh yes, that's right. For this one, they were normal mode data compilations from the RAM website. So normal mode, central frequencies. So also from Van Heist and Woodhouse, yeah. So again, large uncertainties on radial anisotropy in 1D model. That's a compilation of several 3D radial anisotropy models that was published last year by Cheng et al. In this convention, blue means VSH is larger than VSV. Some models, they all have different types of data, different methods for inversion. Some of them are able to constrain anisotropy down to the bottom of the mantle. Others stop at the transition zone. But if I zoom in on the top, which is what we're talking about now, you see that even in the shallow mantle, there's still quite a lot of variations among models. And some of it is thought to be due to the crust, the way the crust is handled, but that's probably not the only thing that's problematic. And then if you go to 400 kilometers depth and 600, you see much stronger variations among models. Some of them, or several of them, have barely any radial anisotropy, or it's very localized. But then others have very strong anisotropy. Whether it's positive or negative in a given region is still absolutely unclear. So that's it for radial anisotropy. Azimuthal anisotropy, as Jean-Paul explained, can be constrained from surface waves. And we have some nice patterns that can correlate correlate pretty nicely with some tectonic features. I wasn't there when he gave his talk, but he probably went into a lot of details on this. And Eric last week gave a talk with his own results that were similar. So the fundamental mode surface waves are really good at constraining anisotropy and velocity in the top 250 kilometers or so of the mantle. But if you want to look deeper, in the deep upper mantle transition zone, you need higher mode surface waves. And so the fundamental modes surface wave would be, so they're shown in here. These are synthetic seismograms. This is the typical Rayleigh wave that you would have seen in intro class, for instance. The higher modes are the wiggles that arrive before the fundamental mode surface waves, and we can separate the seismogram in a certain number of higher modes, and as you go toward higher and higher modes, they tend to arrive earlier and earlier because they sample deeper and deeper structure in the mantle. And you can reconstruct a synthetic seismogram by addition of normal mode. So this is an example from the Visser PhD, where we see the fundamental mode synthetic Rayleigh wave. This is a synthetic based on the fundamental and first overtone, 0 to 2, 0 to 3, and so on. And so you see as you increase the number of higher modes, you get more and more detail in the seismogram. But then at some point, there's not so much difference anymore. So the higher you go in the order of the mode, the more difficult they are to separate. So the study I'm going to present, forgot to mention, this is actually my former PhD student's work, Kai-Ching, is somewhere here, I think. So for this, we used the data set by Visser, where they had they used the model space search approach to measure higher mode and fundamental mode surface waves. They basically were searching and generating velocity models, velocity profiles for many pairs of earthquakes and seismic stations. And from this ensemble of velocity models that fitted the seismograms, they were able to calculate an ensemble distribution of phase velocity measurements for fundamental mode and higher modes, get uncertainties on these measurements, and also they did some statistics to determine how many of these higher modes they were really able to separate. So in the end, they had these several tens of thousands of measurements for Rayleigh wave and for Love wave. I'm not going to talk about Love wave here. But you see they had a lot more measurements for the fundamental mode Rayleigh waves than for the higher modes. And as you go up in the order of the mode, you have less and less measurements because they're more and more difficult to separate. But still, it was enough to generate phase velocity maps. And so this figure shows also the sensitivity of these modes from that data set, that specific data set. You see that the fundamental modes in gray are really good at resolving the top 100, 200 kilometers of the mantle. But the first higher mode is helpful to constrain structure at slightly larger depth, down between 100 and 400 kilometers depth. And as the number of the mode increases, you are sensitive to larger and larger depth. So this data set was sensitive to about 1,000 kilometers depth in structure. So they're useful to map anisotropy and structure deeper, but you'll see also that some of these modes have double peaks. For instance, the yellow here, they have a small peak here, and larger peaks there. So they're also able to improve the sensitivity, the resolution of upper mantle structure, but then there's trade-offs between the top and the bottom. So that's something to keep in mind when you look at the models I'm going to show. So the data, so the Visser and Ampere, they did these phase velocity measurements for fundamental mode, higher mode. They produce phase velocity maps. These are the isotropic part of the phase velocity maps from which you can get 3D models of shear wave velocity, for instance. We're not going to talk about this. What we used is the azimuthally anisotropic component of these maps. So these maps in the frequency domain are azimuthally anisotropic. This can be extracted from the raw data. And then you can use these anisotropic map to map 3D azimuthal anisotropy. And so that's what we did. I'm going to skip all the other technical details, I guess. And I'm going to show you the models right away. So this is the fast seismic direction for vertically polarized shear waves that we found, that we got from our model at 150 kilometers depth. Red is the model, and at this depth we superimpose with the plate motion, absolute plate motion, and we see this has been seen in other models before, that there is a pretty good alignment for the Pacific plate between fast direction and plate motion. This is why we think it's a signature of asthenospheric follow. Then if we go to larger depth here, 300 kilometers, you see that the pattern of the fast direction has changed. The amplitude has also decreased quite a bit. There's a few spots where it's still pretty strong, but generally it's less. The fast direction has changed, generally speaking. And then if we go to inside the transition zone, we see yet a different pattern. So it seems like it's pretty complicated as you go. If you were to visualize this in 3D, it would be a pretty complicated pattern. But something to notice is that the amplitude here in the transition zone has really increased a little bit. And we're going to see this in another figure in a couple of slides. These slides, I realize you probably don't see very much, but this compares, so there's not that many global azimuthal anisotropy models out there. Eric Debye has two here, the two on the left from 2005, and the more recent that he presented last week. This is from Schaefer and Lebedev, 2013, though they have not, I think, published the whole global azimuthal anisotropy model yet. And then this is ours here. So in the very top of the mantle, there's pretty good correspondence between fast directions. The amplitude varies quite a bit between models, so that's not surprising. Regularization will do that. But when we get to larger depth, the amplitude is generally, at least in this model here, and the Schaefer and Lebedev model, the amplitude is a lot smaller, pretty negligible. In this one and ours, there are some regions where it pops up again. And this is a slide by Andrew Schaefer that he showed at HU that was comparing different representation of our model here on the top left. The by 2012, and this was the Schaefer and Lebedev model with high damping, and this one with less damping. And yes, they look quite a bit different. Though if you look really well, you will see how a few features actually are common to these models. There's this one. These show north-south fast direction. Here, east-west, more or less. So if you look really well, you will find some commonalities. Unfortunately, it's not two models that have all the same features. You have to pick here and there. So lots of uncertainties still, but we now have a few models that do have a little bit of anisotropy in the transition zone. One thing that's interesting to do with these models is to predict shear wave splitting. Shear wave splitting, as Maureen talked about, is very good at mapping anisotropy and showing very short wavelength horizontal variations. It's not very good at determining the depth variations of the anisotropy. Surface waves, it's the other way around. They also have very different wavelengths. Shear wave splitting measurements are very localized. Surface waves have much larger wavelengths, so it's really hard to compare them. Here we did predictions. Let me remember now. I don't remember what the white bars are. No, actually. So the red bars are our model predictions from our 3D model. The white bars, I think, were the global spherical harmonic expansions of the shear wave splitting data, which are shown in yellow. You can tell that you don't really know what to do with this. It's hard to compare. But what we can do is to look at the delay times. So this is a figure similar to what Thorsten had done in one of his papers, where we took all these station average shear wave splitting measurements, plotted a histogram in yellow of the delay times, and we predicted the delay times with our model in red here, and with a model from Eric that had mostly anisotropy in the top 200 kilometers or so of the mantle. And you see this is common with many, many surface wave-based models of azimuthal anisotropy. These models tend to underestimate the delay times of shear wave splitting. But with our model, we were able to better reproduce these delay times. There's still discrepancy, but it was a lot better. Now, to be fair, the latest model by Eric, I don't have a figure for this, but to show you, but we've calculated it afterwards. The latest model by Eric that has a much stronger anisotropy in the top 200 kilometers than any other model before is also able to reproduce shear wave splitting delay time closer to what we have. So either we need to have a very strong azimuthal anisotropy in the very top, or we need to have a distribution of azimuthal anisotropy to larger depth to explain the delay times. Now, just to finish and also start, hopefully, some discussions, we took our model and we calculated the average of the strength of the azimuthal anisotropy as a function of depth. And that's the red curve here that you see. So it goes from 0 to 1,000 kilometers depth, and that's the strength of the anisotropy from 0 to 3%. In yellow is Eric's latest model, and I was saying it has stronger amplitude than other models. And in red is our model. So we see, I'm going to focus on the left panel first, we see a few interesting features here. There's some peak of anisotropy at some key depths that are better interpreted in terms of tectonic settings. I'm not going to do that here. We did that in some of our papers. But relatively strong anisotropy, about 2% in the top 100 kilometers or so. Then it decreases with depth. We have a little minimum here, then it seems to be re-increasing a little bit. Don't know how significant that is, but that's about 1.5% of anisotropy. Then between 200 kilometers and the top of the transition zone, it decreases. But instead of continuing to decrease and going to 0 in the transition zone, which is what we might have expected from previous results, we find that it re-increases slightly, up to about 1.5% of anisotropy on average in the transition zone. Then it decreases again to reach a minimum, and then here we're really losing resolution, so I won't discuss this. But another interesting feature of the model is that if you calculate the gradient of the phase direction, so how fast with depth is the phase direction changing, and then you average that over all azimuths and all latitude and longitudes, then you get this curve. So there's lots of wiggles, but if you see a low value in the peaks, it means that the phase direction changes very rapidly with depth on average. So there's some features that, again, are better interpreted in terms of tectonic setting. But what was interesting and very surprising is that we found that there is a peak here about 410 and another peak at about 670 kilometers depth, where we have minima in amplitude of anisotropy. So it means that as we go, we move from the upper mantle down to a transition zone, the anisotropy goes through a minimum, the phase direction changes and then the amplitude re-increases a little bit. Then it goes through another minimum at 670, and the fast direction changes again. So that was very surprising. Still don't know what to do with it, and hopefully we'll have some good discussions about that here. Possible origin of anisotropy in the transition zone, that's a tricky one. Wadsleyite is seismically anisotropic. It's a possible candidate for the anisotropy in the top of the transition zone. However, ringwoodite is, according to pretty much all mineral physicists I've ever talked to, is not seismically anisotropic. So it cannot explain anisotropy in the bottom of the transition zone. So what we're left with, that's really the case, then we need some other mechanism, like a shape-preferred orientation or alignment of something. So one possible maybe candidate would be that we would have some of the slabs might be, so we know that some slabs are stagnating in the transition zone. Maybe the water in the slab or around the slab is causing some weakening the material and possibly causing the anisotropy. I don't know. There's lots of open questions. If the model we have is correct, that there is really anisotropy there, forget about the details of the fast direction at the moment, but if it is there, then the big question is what is it? Why is it there? What is causing the anisotropy? And also, what is causing this change in fast direction? Do we have a change in flow direction, or is it just that the phase transition are doing something to the anisotropy of the minerals that would lead to the observations we did? Is it that there is a change in the slip system? Is there melt, or is there water that could cause do lots of things to the anisotropy? So there is really a lot of work that needs to be done by seismologists. There's very few models so far that have looked at this. So we need a lot more observations, a lot more modeling of anisotropy at those depths, and then lots of work by mineral physicists, rock deformation people, geodynamicists. What could possibly cause such a signal? So I will stop here, and yes, I took a little bit longer. So first, I'd like to have questions from students and postdocs who are not seismologists, so we don't dive into technical details too fast.
Thank you first.
Students and postdocs, one not seismologist.